Let us take some examples to conclude this chapter of rotational kinematics. Example or question number 1 goes to find the velocity and the acceleration of a rod which is pivoted at one of its end. When it swings, through an angle theta, how to find the velocity of this point, that is Vp, and its acceleration. Find the velocity and acceleration of P, that is Ap. In terms of theta, omega and alpha. By using ground frame method. For ground frame method, we need a fixed point. Let this fixed point be pivot. This is the pivot. If L is the length of the rod, the initial position is the final position. This point P has x coordinate, so also a y coordinate. With respect to this pivot or origin, x is equal to L cos theta, y is equal to L sin theta. If you write x is equal to L cos theta, differentiating x with respect to time, you get dx by dt. L, you differentiate cos theta with respect to time, you are getting minus sin theta d theta by dt. We have taken theta and omega in the same order. Omega is taken in the increasing order of theta. Therefore, d omega by dt can be written as plus omega minus L sin theta into plus omega is equal to minus omega L sin theta. This is the velocity. Since x is decreasing, dx by dt can be written as minus Vx. So, this is Vx minus negative direction. Therefore, the x component of the velocity of this point P is equal to omega L sin theta. Which method we are following? Ground frame method. For ground frame method, this is the origin of the coordinate system. I have taken y, down is positive, x in this direction is positive. You can take down positive or negative, it's your wish. Now, take the other component of the displacement or the position, y is equal to L sin theta. So dy by dt is equal to L cos theta d theta by dt. Y increases when the point P swings in a circular path, x decreases, y increases. Therefore, dy by dt is plus Vy. L cos theta, omega is taken in the increasing order of theta. Therefore, d theta by dt is equal to plus omega. This gives us Vy is equal to omega L cos theta. Equation number 2. We want the velocity of this point. We know the x component of the velocity of this point and its y component. The velocity of P is given as Vp is equal to Vx square plus Vy square. What is Vx? Omega L sin theta, square of this plus. What is Vy? Omega L cos theta, square of this. Take the square root of this 2. You are getting Vp is equal to omega into L, and direction is Vx, this is Vy. You add, you are getting Vx square plus Vy square square root. This is the velocity of this point P, and this is must be perpendicular to the rod. Answer. Well, we got the velocity along x direction, we got the velocity along y direction of the point P. By differentiating the velocities with respect to time along the respective directions, we can get the accelerations along x and y directions respectively. Vx is equal to omega L sin theta. Differentiate with respect to time to get the acceleration along x direction. Here omega and theta both are variable. L d by dt of omega sin theta. Here omega is variable, theta also is variable, because d omega by dt is alpha, alpha is given in the same direction of omega. L, you take omega out, or you just differentiate omega with respect to time and take sin theta out, plus now you take omega out and differentiate sin theta with respect to time. You are getting L into d omega by dt is alpha, because you have taken alpha in same direction. The plus alpha into sin theta plus omega, derivative of sin theta with respect to time is cos theta d theta by dt. Since theta and omega are having some direction, or omega is taken in the increasing order of theta, d theta by dt can be written as plus omega. So ultimately we are getting x is equal to L into alpha sin theta plus omega square cos theta. And the y component of the acceleration can be found by taking the derivative of y component of its velocity. The y component of the velocity is Vy is equal to omega L cos theta. The derivative of y with respect to time is equal to L, take common, the time derivative of omega cos theta. Take cos theta out and differentiate omega with respect to time. Then you take omega out and differentiate cos theta with respect to time. And this factor is ay. L d omega by dt is plus alpha, because omega and alpha you have assumed in same direction, plus omega. The derivative of cos theta is minus sin theta, d theta by dt. D theta by dt is plus omega into omega, that's omega square, into minus sin theta. So we are getting alpha cos theta minus omega square sin theta. That's equal to acceleration of this particle at the point P along y direction. Answer. This is a ground frame method, and I can get the same answers by using the relative motion method in the next approach of the same problem. And you can understand here that there is a point of time, or there is a position where the acceleration of this point along y direction will be 0, because L cos theta minus omega square sin theta can also be 0 at a particular point of time or a particular position, and that position can be given by, for a given alpha and omega square, that position can be given by substituting ay is equal to 0. If they ask the question, or simply I ask the question, what is the acceleration of this particle at the point P, the end point of the rod, that is P, as a function of theta, when omega and alpha are the angular velocity and angular acceleration at that position. This is ay and this is x. It is not 0. This can be 0. Let us start doing the problem by another approach called relative motion method. You are getting ay is equal to L alpha cos theta minus omega square sin theta, and x is equal to alpha sin theta plus omega square cos theta into L. Same question, a different approach. Find the velocity and acceleration as the function of theta if omega and alpha are given in the same direction in the increasing order of theta. This point is P, this point is O. With respect to this point, point P moves in a circular path. Since the length of the rod is L, the radius of the circular path must be L. So, R is equal to L. This point P has some acceleration with respect to O along tangential direction and along radial direction or normal direction. The velocity of P is directly given as R into omega, because it is moving in circular path, and R is equal to L. Therefore, the velocity of this point P, Bp is equal to L into omega. Answer. Directly you can get. The acceleration of P is given as AP is equal to APO plus AO. Since this point is fixed, the point O or the pivot is fixed, axis of this point is 0. Then axis of this point P is equal to axis of the point P with respect to the pivot. Since this point P moves in a circular path with respect to the pivot, the axis of the point P with respect to the center of the circle is divided into two parts. One is tangential acceleration and second is radial or normal acceleration, where axis of this point P with respect to O along tangential direction is equal to L into alpha, and acceleration of the point P with respect to along radial direction is nothing but centripetal acceleration, that is L omega square. This is called tangential acceleration. This is called tangential acceleration, and this is the radial acceleration. This can easily be understood by using the concept of kinematics of circular path. When the particle moves with a tangential acceleration. So, this is the tangential acceleration, this is the radial acceleration. The net acceleration of this particle can be found by adding these two accelerations. So, this is the net acceleration of the point P. You add the tangential acceleration with radial acceleration, you are getting the net acceleration of this point P. The end of this rod will accelerate in this direction. Let us now redraw the vectors. This is the radial acceleration, this is tangential acceleration. What is that? This is L alpha and this is L omega square. This is L alpha. The x component of the acceleration of the point P is equal to component of the AR along x direction plus component of the AT along x direction. You add this component with this component, you are getting the AX. Similarly, along y direction, if you take the component of AR, this is called AR, this is called AT. In short, we can write like this. This angle is theta, therefore, this angle is theta. This is 90 degree, therefore this angle is theta. So this component is AR cos theta, this component is AT sin theta, this component is AR sin theta, and this component, the component of the tangential acceleration along y direction is AT cos theta. Therefore, by using the component method, we can calculate acceleration of the particle along x direction will be equal to AR cos theta plus AT sin theta. What is AR? AR is equal to L omega square. Well, the x component of the acceleration, that is x, can be calculated by adding these two x components of the radial acceleration and tangential acceleration. That is A r cos theta plus AT sin theta, and the y component of the acceleration of the point can be calculated by adding the y component of the accelerations AR and AT. These two are AR sin theta minus AT cos theta. But we have taken y, downward is positive, AT cos theta minus AR sin theta. Since both the components of accelerations AR and AT are directed along x direction, the projections along negative x direction, so we can just write minus I cap, or you can write AR is equal to L omega square and AT is equal to L alpha. So L omega square cos theta plus alpha sin theta. Here this is the magnitude, and we got the same thing. Different approach but same answer. Similarly, AY is equal to minus AR sin theta plus AT cos theta in this direction, or you can write downward. If you want to write the vector, that's okay. If you don't write also, you can get this magnitude and direction I have shown vectorially. We do not know if this component is greater than this component, the particle's y direction acceleration will be down. If this component AR sin theta is greater than AT cos theta, the particle's y component of the acceleration will be up. If these two components will be exactly equal, then this particle at this instant doesn't accelerate along the y direction. So AR equal to L omega square into sin theta plus AT is equal to L alpha cos theta. So cos theta alpha minus omega square sin theta in downward direction. You are getting same thing, but approach is different. This approach is called a relative motion method. With this method, we got same answers. Or net acceleration, if you want to calculate, ax square plus ay square square root, or you can just write ar square plus at square. If you add these two accelerations, you are getting the net acceleration. This can be written as, suppose this is ay, let ay be up, and x this is x, this is ay, this is ay. You can write x plus ay is equal to a, or you can write a radial plus a tangential is a. A tangential, a radial plus a tangential, that is a, or you can write x plus ay, that is equal to a. In relative motion method, we used radial component and tangential component, or radial axis and tangential axis as the coordinate axis. In ground frame method, we used x axis and y axis as the coordinate axis. Ultimately, we are getting same answer. We can transform one set of axis to the other set of axis. The radial axis is called r axis and tangential axis is called theta axis. This is r axis and this is theta axis. In ground frame method, we took x axis and we took y axis. Both the methods are self-sufficient. Let's go for the other problem. Well, in last example, in both the methods we used and we got same answer. Let us take another example. Our rolling object this object, say a cylinder, when it rolls without sliding, with a velocity v of its center of mass along x direction, the question is any point P considered on the cylinder will trace a path. Find the equation of the path traced by the point P. Using both the ways, the ground frame method and the relative motion method, let us find it. After that, you can also calculate velocity of the point, distance covered by the point during one rotation. Find the equation of the path traced by the peripheral point. Find the velocity of that point and find the distance covered by the point during one rotation. And of course, you can calculate the acceleration of this point also. But here the assumption is that velocity of the center of the cylinder or disc remains constant. Therefore, omega, which is equal to v by r, to obey the condition of your rolling, is also a constant quantity. Under this condition, find the equation of the path traced by the peripheral point with respect to this origin, this velocity with respect to ground, a distance covered by this point during one rotation of the cylinder. Let us solve the problem by using ground frame method first. Method 1, ground frame. The disc or the cylinder was here. This is the point P at time t equal to 0. The lowest point of the cylinder, let it be P. And that point was lying on the origin of the coordinate system x and y are the axis of the coordinate system. This point P is the lowest point of the rolling cylinder. This is the scenario at time t equal to 0. Let us assume that the cylinder rolls for some time without sliding. After time t, this point P moves from this point to this point, following a path given by this dotted line. With respect to the center, C of the cylinder, this point P revolves through an angle theta say. At time t equal to 0, P was here. After time t, P comes from the bottom to this point. You can imagine the point P as an ink mark. You just press your pen, the nib of the pen at the bottom of the cylinder, you can get a mark. Let this mark be P. As the cylinder rolls, this mark moves in a particular curve given by the dotted line. This point P moves from this position to this position. While doing so, this revolves through an angle theta with respect to the center of the cylinder. Let us assume that the x distance or the x coordinate or the x displacement of this point P with respect to this fixed origin be x. And the y distance of this point P with respect to this origin, let be y. So you can call this is y and this is x. Since this distance is none other than the radius of the cylinder, and this is r cos theta, y can be written as r into 1 minus cos theta, and x is equal to the distance covered by the center of mass is equal to v into t, because velocity of the center of mass is v. The center of mass moves with constant velocity. During the time t, it moves through this distance. That's equal to vt. Therefore, this distance is vt, and this distance is, if this is r, and this is theta, this is theta, this distance is equal to r cos theta. Now, this is r cos theta, this is r sin theta. This is r cos theta. This distance is r cos theta. This distance is r sin theta. And this distance is Vt. Therefore, x is equal to Vt minus r sin theta. So, in terms of theta, we can find the coordinates of this point P. This point P has coordinates x, y, let after time t. Let the point P be at the origin, or let the point P lie at the origin. At t is equal to 0. After a time t, the center of mass, say, moves through a distance Vt, and the point P revolves through an angle theta with respect to the center. As a result, the coordinates of the point P at time t are given as x is equal to Vt minus r sin theta. The center of mass goes through the distance Vt, and this point P comes back with respect to the center of mass through a distance r sin theta. As a result, the point P will be closer to the origin by a distance x, that's equal to Vt minus r sin theta, and the y coordinate, or it is above the origin through a distance y is equal to r into 1 minus cos theta. Since for pure rolling V is equal to r omega, we can write x is equal to, instead of V, we can write r omega into t minus r sin theta. Since velocity is constant, omega also is constant, because omega is equal to V by r, that is also constant. This means that with respect to the center of the cylinder, the point P moves in a circular path and executing uniform circular motion. The point P executes uniform circular motion with respect to the center. Therefore, theta is equal to omega into t. This omega t can be written as theta. So, r theta minus r sin theta. Therefore, I can write x is equal to, take r common, theta minus sin theta. And y you can write r into 1 minus cos theta. Once you obtain all these coordinates, x and y coordinates, our mathematics, the coordinate geometry states that when a point moves such that the coordinates are x is equal to r into theta minus sin theta and y is equal to r into 1 minus cos theta, the nature of path traced by that point is a cycloid. So the path will be traced in this way. This is a cycloidal. And at this point, the point P will reach the highest position and the disk will come to this position, or the cylinder will come to this position. This highest point will be the position of the point P. The ink mark, the point P, will reach the highest position, and the center of curvature of the path, that is cycloid, traced by this point P at the highest position, will be equal to 4r. This is the center of curvature, let it be seen as. This is equal to 4r, that is radius of curvature, what we obtained in the last example. Whereas this r is the center of curvature of the path traced by the point with respect to the center C. With respect to the center C of the cylinder, this point P moves in a circular path. Therefore, the radius of curvature of the circular path is the radius of the disk itself or radius of the cylinder itself with respect to the center of curvature C. But with respect to ground, the center of curvature is C dash of the path traced by this point, that is none other than the cycloid. So the path is cycloidal with respect to ground, and the path is circle with respect to the center of the cylinder or center of the disk. Next, to find the velocity. The first part is over. The nature of the path traced by the point, the ink mark, is cycloid. So let us differentiate both x and y with respect to time. Velocity of the particle along x direction, velocity of this particle or the point P along x direction is equal to dx by dt. Method is ground frame. So x and y are the coordinates of this point P with respect to ground frame or with respect to the origin fixed to the ground. Dx by dt is equal to v minus r cos theta d theta by dt. D theta by dt is omega. Omega into r is v. So we can just write omega r cos theta. But omega r is equal to v for pure rolling. So you can write v into 1 minus cos theta is the velocity of the point P along x direction. Equation number 1. Next, differentiate y with respect to time to get the velocity of this point along y direction. That's equal to r sin theta cos theta derivative minus sin theta minus into minus plus into d theta by dt, because with respect to time we are taking the derivative. D theta by dt is omega. So this omega into r sin theta, and omega r can be written as v sin theta. So vy is equal to v sin theta, equation number 2. After getting these two components, the velocity of point P is v is equal to vp is equal to vx square plus vy square. That's equal to v1 minus cos theta square of this plus v sin theta square of this, square root of the entire term. So Vp is equal to out 1 minus cos theta whole square, 1 plus cos square theta minus 2 cos theta plus sin square theta. Cos square theta plus sin square theta 1, 1 plus 1, 2, 2 minus 2 cos theta, that is equal to 2v 1 minus cos theta square root. 1 minus cos theta square root can be written as v into 1 cos square theta plus sin square theta is 1, 1 plus 1, 2. So this 2 must be kept inside the square root. 1 minus cos theta square root can be written as 2 sin square theta by 2 into 2 square root of this whole into the v. This gives us velocity of the point is equal to 2v sin theta by 2. By applying ground frame method, we got this velocity of this peripheral point as the function of theta. You can of course write theta is equal to omega t, and omega you can write v by r because it is rolling perfectly, or you can write 2v sin vt by 2r. That is the velocity of this point P as the function of time, velocity of the point P as the function of theta.